I gave my book, Grokking Relational Database Design, to an AI tool, NotebookLM, and asked it to generate an audio overview. After a lot of trial and error, I had to do something strange. Delete the first two chapters. Those chapters help readers pick up the essential SQL skill required for database design, but for some reason, NotebookLM couldn't move past them. Once I removed them, it finally worked. But even then, it missed something big, which is how AI itself can help you design better databases. That's a key theme in the book, and the overview completely missed it. In this video, you'll hear the final AI-generated overview next. Then, I'll break down what it got right, what it missed, and where AI actually fits into modern database design. And if you would rather skip the overview, just jump ahead to the afterthoughts.
Ever wonder how all the information you see online in apps like everywhere is actually organized?
It's a good question. It often seems like magic, but there's a solid structure underneath.
Totally. And today, we're cracking open that structure, database design. It's the foundation of digital order.
Exactly. Think of it as the architectural blueprint for information. A well-thought-out database is what makes pretty much everything run smoothly.
Right. And our guide for this is Grokking Relational Database Design. It's packed with insights.
It really is a great resource for getting the core concepts.
So our mission today is to walk you through the essential steps how a database goes from just an idea to a real working system. We want to give you that core understanding without getting totally bogged down in the super technical stuff.
Sounds good. It's a process, definitely.
So where do we even begin? What's step one?
Okay, step one, the absolute first thing, is understanding exactly what the database needs to do. It's all about requirement gathering.
Requirement gathering. Okay, so before you even think about tables and code, you need the big picture. Like, what's its job?
Precisely. You've got to talk to the people who actually use it, the stakeholders. And you look at how they're doing things now. Maybe they're using spreadsheets or paper forms or, sticky notes.
Yeah, maybe. So you're digging into their current world.
You are. For example, if we were building a system for, say, a sci-fi fan club, like the Sci-Fi Collective mentioned in the source, we'd ask how they track members, events, maybe merchandise.
Okay, so what kind of questions help you pull that information out? It can't just be, what data do you need, can it?
Definitely not. You need to ask things that reveal what data needs storing, how it connects, and crucially, what rules apply. Like, can a member have multiple email addresses? Does an event have to have a location? You're listening for the key things, the subjects.
Subjects, like the main nouns they talk about.
Exactly. Nouns are a huge clue. The book calls them subjects initially, and the characteristics, what describes them. There's a neat little test that or owns a test.
Okay, tell me more.
Well, if someone says a user has payment information, then user is likely a subject, and payment information is a characteristic. The book uses user and order. A user has contact details, an order has product info, and a total price.
Got it. So you're listening for those relationships, but what if people are vague? Or they don't really know what they need yet?
Oh, that happens all the time. It's normal. That's where you gently probe, ask why. Ask for examples. Can you show me what you mean? And asking for sample data, like seeing an actual spreadsheet they use that's gold, it clarifies things way faster than just talking abstractly.
Seeing is believing, kinda?
Pretty much. And it's not just the subjects and characteristics. You also need to map out how they connect to each other right from the start.
Ah, the relationships. Like one customer can place many orders.
Exactly. Is it one-to-one, one-to-many, or many-to-many? Figuring that out early is fundamental. Like, one user might write many reviews, but one review is written by only one user. That's a one-to-many relationship.
Okay, so lots of talking, listening, and clarifying. Then what, once you've gathered all that intel?
Then you move into the next phase, analysis and design. This is where you take all those requirements, all that understanding, and you start creating the actual blueprint, the formal plan.
The blueprint. Okay, so the subjects and characteristics get formal names now.
They do. Subjects generally become entities, which you can think of as your main tables, and characteristics become attributes, which are like the columns in those tables.
Entities and attributes.
Got it.
And naming them, is that important?
Oh, definitely. Consistency is key. The book mentions a few styles like snake case, which uses underscores, or camel case. The book prefers snake case. Whatever you pick, you just got to stick with it.
Right, don't mix and match.
And another big thing, avoid using reserved SQL keywords. Words like order or table have special meanings in the database language. So if you need an order entity, maybe call it purchase or customer order instead.
Good tip. Avoid confusing the database itself.
Okay.
Okay, now, keys. Always hear about primary keys, foreign keys. What's the deal there?
Keys are absolutely crucial. They do two main things. Uniquely identify each record, like each specific customer or order, and link related tables together.
All right.
First, you identify candidate keys. These are any attribute or combination of attributes that could uniquely identify a row. For a user table, maybe the username, the email address, and a unique user ID could all work as candidate keys.
So, multiple options, potentially?
Potentially, yes. Then, from those candidates, you choose one to be the primary key. That's the official identifier for that table. Often it's just a unique ID number, like userid.
Okay, one primary key to rule them all for that table. And how do they link tables?
That's where relationships and often foreign keys come in. We already talked about identifying the types of relationships one-to-one, one-to-many, many-to-many.
Right, like users and orders.
Exactly. To actually implement that one user, many orders link, the orders table would typically have a column, say userid, that stores the primary key of the user who placed the order. That userid in the orders table is a foreign key. It points back to the users table.
Ah, okay, so the foreign key is the connector.
It's a connector, and it helps enforce the relationship. And we often use diagrams, like with crow's foot notation, to visualize all the entities, attributes, keys, and relationships, including the cardinality, like 0 or more, 1, and only 1.
Crow's foot. Sounds interesting.
It just looks a bit like a bird's foot at the end of the connecting lines, showing the many side of a relationship. And for those tricky many-to-many relationships, like orders and products.
Yeah, one order has many products. One product can be in many orders.
Right. You typically create a third table in the middle, a junction table, maybe called order products. It would hold pairs of order IDs and product IDs, linking them together.
Okay, that makes sense. It handles the complexity. Now, another big word, normalization. What's that trying to achieve?
Normalization. It's basically about organizing your data efficiently to reduce redundancy, having the same information stored in multiple places, and avoid potential inconsistencies. You want well-structured tables where information lives in one logical place.
So tidying up again, but on a deeper level.
Exactly. The goal is to make your data reliable and easier to maintain. The book talks about aiming for something called voice code normal form, or BCNF. It sounds technical, but the core ideas are: each table has a primary key, you don't stuff multiple values into one column, and every other column in the table depends only on the primary key, not on other non-key columns.
Okay, can you give an example of that last point, depending only on the primary key?
Sure. Imagine you had an employee table with employed, the primary key, departmented, and also department name. The department name really depends on the departmented, not directly on the employed. That's a transitive dependency. Normalization says you should probably split that out, have an employees table and a separate departments table linked by departmented.
I see. So each piece of info is directly tied to the table's main subject. That makes sense for avoiding update issues.
Precisely. If a department name changes, you only change it in one place, in the departments table.
Okay, good structure. What about keeping the data safe? Security came up.
Hugely important. Security-oriented design is woven in. You need to prevent unauthorized access, modification, deletion. Encryption is a big one, especially for sensitive stuff like payment details. The rule is, store the encrypted version, never the plain text.
Never plain text for sensitive data. Got it.
And then there's access control. Who gets to see what? Who can change what? Concepts like role-based access control mean you grant permissions based on someone's role, like administrator or customer support rep, rather than managing permissions for every single user individually.
Right. Different roles, different permissions. Makes sense. Okay, and performance. We want this database to be fast.
No, absolutely. Slow databases are frustrating. Performance-oriented design looks at things like indexing.
Like an index in a book.
Kind of, yeah. An index on a database column, say the rating column on a movies table, helps the database find movies with a specific rating much faster without scanning the entire table. It speeds up searching and sorting.
So it's an extra structure to speed things up.
It is. And sometimes, though less common, you might do the opposite of denormalization. Intentionally adding back a little redundancy to speed up specific, very common queries that would otherwise need to join many tables together. It's a trade-off. Use carefully.
A calculated risk, maybe.
You could say that. You sacrifice some normalization purity for speed in specific cases.
Okay, wow. So analysis and design cover a lot. Structure, keys, relationships, tidiness, security, speed. Once that blueprint is solid, what's next? Building it.
Exactly. Implementation and testing. You take the design and translate it into a real database using SQL, the standard database language.
SQL time. So create table and all that.
Yep. You create the tables, define the columns, and specify the right data types like varchar for text, int for whole numbers, decimal for currency, timestamp for dates and times. Choosing the right type is important for efficiency and correctness.
And you add rules,
Right.
constraints.
Yes. Constraints enforce your design rules. Not null means a column must have a value. Primary key ensures uniqueness. Foreign key enforces those table relationships, ensuring you don't have, say, an order referring to a user that doesn't exist. That's called referential integrity.
Preventing orphans in the data.
Good way to put it. Then you have unique for columns that aren't the primary key but still need unique values, like email addresses. And check constraints let you enforce custom rules, like making sure an age value is positive.
Lots of ways to ensure data quality. And then test, test, test.
Absolutely critical. Does it work? Can you add, update, delete data as expected? Does it perform well under load? Are the security measures actually blocking unauthorized access? Testing validates the whole process. You need good SQL skills here, too, for both building and testing.
Wow, okay. That's quite the journey from idea to working database. Requirement gathering, the deep analysis and design covering relationships, normalization, security performance, and finally, implementation and testing.
That's the core flow, yeah. Understanding those phases really gives you a solid foundation, whether you're designing databases yourself or just using applications that rely heavily on them, which is pretty much everything these days.
It really is. This has been super insightful. It makes you appreciate the thought that goes into even simple apps. So for everyone listening, maybe think about how these ideas, structure, relationships, consistency apply to organizing information in your own world, work, or personal. Could a bit more design lead to more clarity?
It's a great takeaway. Thinking about which part of this process, from requirements to testing, you found most interesting can tell you a lot, too.
Definitely food for thought. Thanks so much for walking us through that.
My pleasure. It was fun to dive into.
Now that you have heard the AI-generated overview in the podcast form, let's talk about 3 things, starting with how well it actually covered the book. Here's a full list of topics from the book, grouped into 3 major sections. The overview skipped the first section on SQL foundations and the last section. So for topic coverage, I would give it a 2 out of 5. Next, let's talk about structural coherence. Overall, it's acceptable. The flow mostly makes sense, but there are gaps and inconsistencies along the way. So I would give it a 3 out of 5. Last, let's look at conceptual accuracy. The overview mostly stays on surface and skips the parts that really require precision. So I would give it a 2.5 out of 5. Overall, the audio overview is acceptable. But remember, I had to remove the first section of 2 chapters just to make it work. It seems like the model doesn't juggle multiple topics, or it fails to connect SQL to database design properly. So what did the overview miss? Ironically, it missed everything about itself, how AI can help speed up database design. This theme is interwoven throughout the book and highlighted in the final section, but the AI overview skipped it entirely. You might be curious about how AI actually helps, but that's a big topic. So instead, let's start with a quick snapshot. What AI is good at, okay at, and terrible at when it comes to database design. So what's AI actually good at? Quite a few things, like turning requirements into draft entities and attributes, or generating SQL code from a design, or creating sample data to test a database. In short, AI excels at tasks that are labor-intensive but don't require much judgment or decision-making. What's AI just okay at? Tasks that involve some judgment, like choosing primary and foreign keys. It can suggest decent options, but not always the best ones. For example, AI often defaults to auto-increment IDs, even when natural keys would be much better. It can also help with normalization, but mainly in simple cases. If you got a circular relationship across 3 entities, you are better off doing that yourself. When you have some tasks that are somewhat complex and ambiguous, AI can still help but would be less reliable. AI does make reasonable guesses, but it also makes assumptions and won't ask for clarifications. So for anything somewhat complex or ambiguous, you still need to stay in control. Finally, what's AI terrible at? Trade-offs and deep design decisions. Things like denormalization, redesigning for performance, or choosing the right indexes. These tasks require context, judgment, and experience. That kind of insight can't easily be put into words and fed into a model. And even if you try, AI tools have a limited memory, struggle to integrate complex requests, and often hallucinate as things get more nuanced. In short, AI can help speed up the early stages of database design, generating ideas, drafting schema, or even writing queries. But if you want to design something that's solid, scalable, and real-world ready, you still need to drive the process yourself. And that's exactly why I wrote the book Grokking Relational Database Design, to explain not just how to design databases, but how AI can support the process in real world. And now, I'm about to turn it into a video series. Each episode will walk you through a core concept, from requirement gathering to schema design to normalization, with practical examples and an eye on how AI fits in. If you want a structured, modern approach to database design, check out the book in the first comment and subscribe for the series. Thanks for watching.